We continue to discuss different problems, different applications on continuity equation. So far we have considered a few problems that were either two-dimensional or three-dimensional, but all rectangular in their geometry. Here we consider a circular type of motion, or what we call as line vortex. The question that we consider here is two-dimensional, so it's a two-dimensional motion. Incompressible, will be incompressible, that means no change with respect to density. Vortical flow means that it is related to somehow the vortex, and how that vortex is being represented in mathematical terms is given in the question. The problem that we are considering is consider a two-dimensional incompressible flow in cylindrical coordinates. The tangential velocity component u theta is given as equal to k by r. K is some constant, so u theta is changing as 1 by r. That means it is inversely proportional to r. As r increases, the u theta decreases, and as r decreases, u theta increases. This represents a class of vortical flows. Generate an expression for the other velocity component that is in the radial direction, and we denote it by ur. Now, how to start? Again, we start with the continuity equation, but this time we start the continuity equation in radial coordinates. And again, since this is a two-dimensional motion, nothing coming from the z component, because the z component does not exist, and therefore that term is deleted, and we are left with only these terms, and which implies this. Since we have to calculate ur, so what we want to determine, we keep it on the left hand side and take the other terms on the right hand side. If we do that, then we integrate it with respect to r, because we want to calculate ur. So therefore we integrate the equation with respect to r. When we integrate it, we obtain our ur plus 0, because there is no r term coming here, and in fact, and then there will be some constant of integration. That constant of integration we keep in a way that it can be depend on the other variables such as theta and time t. And of course, since this is there may not be any t contribution coming, any time changes coming in here, therefore any function that we write as f theta t will work or should work. And therefore the value of ur here can be written as ur is equal to f of theta and t, or that is f divided by r. You can see that this is r ur into f is equal to f. So if I keep only ur here, then this r is taken in the denominator, and therefore this term as you see it. So thus any radial velocity component of this form will provide us with a two-dimensional incompressible velocity field, and it will satisfy continuity equation. We can confirm it. It's always good to see and to confirm that the continuity equation is identically satisfied. We consider again the different situations that may occur here. For example, if f is equal to absolutely 0, that is the value of constant is equal to 0, then u theta is equal to k over r, and we call it as line vortex that we have discussed when we were considering kinematics of fluid flow. And another possibility is that, okay, this is not 0, but some absolute constant like 1, 2, 3, minus 5 or something like that, and then a different flow field will occur, different streamlines will be reflected when we draw the graph. So there can be more complicated functions also that can satisfy this continuity equation in such situations. If the function f that is assumed to have been depending upon theta and t actually depends on one of these variables or both of them, and then in that case, of course, the function become more complex and the flow field will be more complex and could be dealt as and is required. If we try to draw the field, then you can see the streamlines and flow field for a line vertex in case A. That means when we have considered f to be equal to 0, you can see that u theta is taking the maximum value here when r approaches 0, and it is reducing as r increases. So the velocity is therefore, but if you draw the streamline, it's going in circles, and the circles are uniform circles. We call them as line vortex. So you can see the motion is quite circular in its shape, in its geometrical demonstration, and they are all circles about the origin. If it's some constant, if f is equal to, there is some absolute constant, then in that case, ur will have some value c over r, and u theta is equal to this. If we are giving some values to it, then as we draw it, what we get is a spiraling line vortex, or what we say as sink flow. In our kitchen, for example, if the water is flowing down into the sink, we see this kind of motion. So this is another example of a different type of circular flow which satisfy continuity equation.